Yes, any doubt in the timing diagram part?
Sir, last class the sir discussed about the finance states, how to design.
FSM.
Yes, they discussed about the FSM, yes, designing of the finance status
Okay.
by using flip.
Mhm. So FSM is completed, or basically they want to discuss that in the next class they will discuss.
Actually, he taught us about regarding how to design that.
Mm-hmm.
Yeah,
Okay. Mm. So I think they discuss FSM. In this, they discuss that how we decide the structures. Like for example, we are giving the multiple states are available. Mm. Like there are the zeros available, one is available, two states are available. Okay, any particular state I just define. Mm. With this 0 to 1, I can go when input is 1 and output is 1. Okay, and from 1 to 0, we go when input is 1 and output is 0. Similarly, if input is 0, output is 0, and when input is 1, output is 1. Okay, so like for example, we are taking two states, one is the 0 and second is the 1. Now, with respect to the 1 and 0, there are two inputs is possible. One is 0 and second is the 1. Similarly, with respect to the 1 state, again two input is possible, 0 and if 0 is coming, the next state will be 0. If 1 is coming, the next state is 1. Similarly, with respect to 1, if 0 is coming, sorry, if 0 is coming, next state is 1, and if 1 is coming, next state is 0. Okay, I just take this one. Now we have to design this with the help of flip flop. Okay, so in the particularly is this FSM, when we design with the flip flop, there is one particularly table we decide we discuss, truth table, correct access table, and then excitation table. Where we define the what is the qn and what is the qn plus 1. With respect to this, if I design with the d flip flop, I can draw this table. Okay, and with the help of this table, I can design this FSM machine, finite state machine. Professor, in the last class, sir discussed this thing.
yes, sir.
Okay,
So this
they have already
actually, sir,
discussed.
the difficulty comes when we have to draw the state table, what you
Uh-huh.
can say, the state diagram,
Uh-huh.
and it's pretty difficult. But sir, explain it, and from that state diagram, we have to make the state table and then transition table and then excitation table.
Mm-hmm.
Then that part was little bit confusing, or you can say what, chaotic.
Okay. Like for example, if I say that
Means if you have given one
we are
input,
giving a two inputs, okay,
if the input is
with that
given,
two.
and from that input we have to derive the output by the state diagram. From the state diagram, we have to derive that output. So it
Mhm.
becomes difficult.
Like there are the two input state are available. So four possible situation are available. Okay, because if we say the two input states, so 0 0, 0 1, 1 0, and 1 1. Four particularly states will be possible. Okay. Now what we define that with the 0 0, two possibilities are there. Now the next input is either 0 or 1. If it is a 0, so it will be remain as a 0 0. If it is a 1, it will be go to the 0. Okay. Uh, okay. If 0 1, 0 and 1 at 0, it will be go to the 0 0. At 1 1, it will be go to the 1. At 1 0, 0 and 1, when it is a 0, it will be go to the 0 1, and at 1 1, it will be remain as a 1 0. No. Okay. Mhm. 1 1. Okay, and 0 and 1, when it is a 1 1 0, it will be go to the 0 1. Okay, like for example, in this way I just define. Okay, now with the can I draw that particularly this one? So when 0 0 input is 0, it will be remain at this place. Okay, and when 0 0 input is 1, it will be go to the 0. Okay, now 1 0, it will be 0, so it will be go in this direction 0, and 0 1 1 becomes 1. 1 0 0 becomes 0 1, and 1 0 1 becomes 1 1. Okay, and 1 1 becomes 0 becomes 0 1, 0, and 1 becomes 0. Okay, so like for example, any particularly FSM finite state machine will be available. On the basis of this one, we can design this type of state matrix. Okay,
Yes.
now after designing this state matrix, now here you can see that there are two direction state matrix is possible. Two direction state matrix I just defined. Okay, but in generally it is a unidirectional. Okay, so if I say that my present state is what, present state is 0 0. So next state is what, from 0 0 it will be moving to 0 1. Okay, now similarly for 0 1, the next state is either 0 0 or 1 1. Okay, both next state is possible in this diagram, but generally it is a unidirectional. So basically either in the one direction, either it will be go to the 1 1 or it will be go to the 0 0. Okay, so like for example, I just change this diagram and consider that this particularly the thing, remove this thing. Okay, remove this thing. Now I am considering only this one. Okay, now when it is a 0 1, so next state is 1 1, the direction is 1 1. Okay, now after the 1 1, the next state is 0 0. Next state is 0 0. Okay, only three states are possible. Okay, only three states are possible. Now, with respect to this one, I can write down the equation for this one. I can write down the equation of this one, and with respect to this one, I can write down the equation of this one. These two, basically these two are okay. So if I say for this one, can I consider as a, if I take as a, this one is available in this two positions. So if it is here, y1, y0. So can I write down a y1 plus y0? Okay, addition of these two positions. So what is next at d naught is nothing but y1 bar plus y. Similarly, when I solve this one, so for this one, can I write out as a y1 xor y naught? Okay, XORing, because there are two 0 0 0 0 1 output is 1 and 1 1 output is 0 if we are using the XOR gate. If we are using the XOR gate. Okay, so we are getting, this is our D0 and this is our D1. So we write the equation for D0 and D1. D0 is y1 plus y0 bar, or we can say the y1 y0 whole bar. And D1 is y1 x over 1. Okay, now if this is a D flip flop, so this is the D0, this is the y0. Okay, if we are using one more flip flop, so it is a D1, it is a y1. Okay, clock will be same clock. Now what is the equation of D0? That is the y1 and y0 we are taking. Y1 and y0 we are taking. We are using a NAND gate and apply on. Okay. Similarly,
We are drawing on the basis of that state diagram.
yeah, on the basis of the state diagram.
And then, sir, you have taken the table.
Table I
It's
just
actually
taken as
depend.
a table I am just taking as a randomly. Okay, here I take this
So it
table
is
that
random.
you draw. Yeah, I am taking this one as a randomly, but you can see that when I draw this particularly table, so there are two particularly dimensions, like from 0 0 to 0 1 and 1 0 1 to 0 0. Again, you can go into the backward direction. Okay, so that's why I remove this particularly path and not consider this table. Okay, but now in the future we discuss one table also. Okay, with the table also
So means here when the
we are
input is
using with the state diagram, only state diagram. We are not
we are
considering this one. We are not considering this one. We are only considering this one. Okay. Clear?
Yes, sir.
Now, what is D1? D1 is Y0. Y0 we are getting from here, and Y1 that we are getting from here. We are using the XOR gate and connect on to. You can connect on D1. Okay. Any doubts? Using a state diagram.
So by using state diagram, we can directly draw the FSM. There's need of excitation and transition table.
The need of excitation and transition table is that wait a minute. I'll just explain this thing also. Yeah. Now what we decide, what we choose is that we only define that we only draw this particularly FSM for the next state. Okay. We only draw the FSM only for the next state, because we what we do, if we are considering this is the D naught, okay, we only draw this equation for the D naught in terms of previous transition. That means what is the next state, we will decide according to the present state. Okay.
Okay. Also, we have not considered the inputs also, no?
Yeah, we are
Input
not
is
considering any input. Also, we are not considering what is the mm, different conditions, or basically what is the movement of that particularly part. Okay, so for this one we go with the excitation table.
the excitation or the transition table. It is taken when we have to find the output and the whole.
Exactly,
Okay.
exactly. We are taking one more case. Like this state. I think in your graded assignment week 12, any question related to the FSM? Let me check some particularly question. Yeah, we are taking one example. Just wait a minute. I just take one example, better example. Mhm. We are taking we are taking with the table, state table 0 0. The two states. Okay, and one input. So input is also 0. So then the state 0 0 and input that we consider as 0 0 0 1 0 1 0 0 1 1 1 0 1 1 1 0 and 1. Okay, now with respect to this one, we are defining the next state. Okay, in the next state, what we consider that if my next state would be like, for example, I just draw one diagram. So it is a 0 0 0 1 1 0 and 1 1. Four states are available. When input is 0, when input is 0, okay, and when input is 1, okay, from 1 0, when input is 0, this one, and when input is 1, it will maintain as a 1 0. For 0 1, when input is 0, it becomes 4 to the 0 0. When input is 1, it will be 4 to the 1 1. Okay, and when 0 0, when the input is 0, it will be remain as a 0 0. Okay, and when it is input is 1, it will be go to the 0. Okay, so this is your FSM, state transition. Okay, now with respect to this one, can I draw this table? The present state is 0 0, input is 0. What is the next state? It is a 0 0. Okay, now When it is a 0 0, input is 1, it will be moved to the 0. Okay. On 0 1, when the input is 0, it is go to the 0 0. 0 1, input is 1, it will be moved to the 1 1. Okay. Now 1 0, the input is 0, it goes to the 0 0. 0 1, input is 1. 0 1, input is 1, it will be remain as a same 0 1. Sorry, 1 0. 1 0, input is 1, it is remains a 1 0. Now 1 1, when the input is 0, it go to the 0 0. When input is 1, it go to the 1 0. Okay, you have defined this table, current state elements. Clear? Now with respect to this one, output also defined. Okay, and with respect to this one, output also defined. If you see in the if you see in the state transition matrix, this is the 0 oblique 1, 0 oblique something 0 or 1. Okay, so this is the input and this is the output part. Mm. So what we consider in this situation is that if input remains mm, now what we consider that if input uh, with respect to the input, if we go to the initial state, if we go to the initial state, output is 1. Output will be considered as a okay, or maybe in question some equation will be also given. Like for example, in the question it is given that y is equal to a plus b times x. Okay, a plus b times x. If it is given, on the basis of this one, we calculate what is the output y. Okay, output y. So like if I am taking the a plus b times x, so a plus b is what? This a plus b. So here a plus b, a plus b. So output is 1. Okay, here we can say the a plus b is 1, a plus b is 1, but output multiply with x 1. A plus b is 1, multiply with x is 1. So all three particularly position output is 1 and remaining the output is 0. Okay, or it is given that a plus b bar multiply by x. Okay, a plus b bar multiply by the x. So if we are considering this one, so a plus b bar, so b bar is this one, b is this one, so all these one are 1 1. Now 0 plus 1 become 1 and multiply with 1, so here the output is 1, this output becomes 0. Okay, so any equation, output equation given in the question, so we can calculate the output of that one, FSL. Okay, so now we draw this table. Okay, now we design this particularly with the help of D flip flop. We design this one with the help of D flip flop. So in the D flip flop, what we consider, we are considering the present state and next state. So A n this one, B and this one. Next is it A n plus 1, B n plus 1. So an and an plus 1. Okay, with respect to this one, an and an plus 1. With respect to this one, we can calculate the d. We can calculate the d. So yes, calculate the d. Now we required a excitation table of the flip flop that we discussed in the flip flop part. Similarly, with respect to bn and bn plus 1, we calculate the dn. Okay, that comes from the excitation table. That comes from the excitation table. Okay, you remember the excitation table of D flip flop? So excitation table D Qn plus 1. So D is 0, Qn is 0, Qn plus 1 is 0. D is 0, Qn is 1, Qn plus 1 is 0. D is 1, Qn is 0, 1, and D is 1, Qn is 1, 1. Okay, so this is the truth table. Now if we draw the excitation table, so Qn plus 1 and D. So when both are 0, 0, 0, 1, 1, 0 and 1. So when 1, 1, it is a D. When it is a 1, 0, it is a 0, it is a 0, 1, 1 and 0. Okay, 0, 1, 0, 1. This is the excitation table. Okay. Now can we draw the excitation table here? So present is 0, 0, we are getting a 0. It is a 0, 0, we are getting a 0. It is a 0, 0, we are getting a 0. It is a 0, 1, we are getting a 1. It is a 1, 0, we are getting a 0. 1, 1, we are getting a 1. 1, 0, we are getting 0. And last 1, 1, we are getting. So this is the, for a and an plus 1, we are getting a q1. Okay. Now for the bn and bn plus 1, we are again getting a dn. So 0 and 0, 0. 0, 1 becomes 1. 1, 0 becomes 0. 1, 1 becomes 1. 0, 0 becomes 0. 0, 0 becomes 0. 1, 0 becomes 0. And last is the 1, 0 becomes 0. This is the excitation table of with respect to bn and bn plus 1. Okay. Now in the case of D flip flop, in the case of D flip flop, we know that only one input is possible. Only one input is possible. Okay, because this is the D. We are getting first A flip flop. So we are getting the AN. Again D with the second flip flop. We are getting a BN. Okay. Any doubt?
No, sir.
Okay. Now we have to combine A and B both for considering as a D. For considering as a D. Mm, Now, if you see this one, mm, with respect to an and an plus 1, an and an plus 1, can we write a equation for dn? Okay, so an and an plus 1 is 1 at this one, and this one. That means this, this. Okay, so this is 0, 1, 1, 0, and 1, 1. So simply the equation is what? Simply the equation is what? A plus B. 0, 1, 1, 0, and 1, 1. This is the condition of A plus B. Okay, and every time the x is also 1. X is also 1. So I just multiply with the x because input is also important. An plus bn time x. Okay, and when we draw with respect to the bn and bn plus 1, what is the dn here and here? So that's in this condition and this one. So that condition is an bar plus bn bar, 3n bar bn bar, and this condition is an bar bn. Multiply with the x. Multiply with the so an bar I can take as a common. So that is simply the an bar multiplied by the x. This is the for D. Okay. Now can we have the an and bn? Okay. Can say calculate for the dn? This one. Okay. With the help of this one, we use this particularly as an input of dn. Okay. And with the help of this one, we use this dn for this one. Why? Because this dn is considering the an and an plus 1. That means an is where an comes? An comes from here. Okay, an comes from here. So that particularly the first dn is equation will be implementing for first flip flop. Second is calculated using the bn and bn plus 1, and where bn comes from the second flip flop. So that means the second equation will be implemented for the second system dn. So like for example, we are saying that this is the an. Okay, so I'm taking this as the an. Okay, and this an is multiplied with the x, and from here we are taking as a bn. So an multiplied with x input, ending of these two. Okay, this x and bn, again ending, and then ORing of these two. Okay, ORing of these two and use that particularly for this. Okay, don't be confused which dn we are using this one. Okay, because both are the dn and dn. So don't be confused where dn, this dn is used and where this dn is used. The first dn, that is consider using the excitation table of an and an plus 1. Okay, that particularly is using for an and an plus 1, and where an comes from the first one. So that's why we are using this dn for an first one. Okay, now second dn is the an bar. So an bar also comes from here. An bar and x, directly ending of these two, and goes for this two. Okay, if an bar is not available, what we do, we have to use one NOT gate. Okay, an in the input and NOT gate. So an bar we are getting, and after that we are using the AND gate of an bar dot x. Okay, any doubts? Now you understand where we require the excitation table.
Yes, sir.
Okay, we require the excitation table for dn equation.
And that state table means it is not for DN, then it is for what?
State table is basically only dependent on the present state and the output current state. Basically, it is dependent on the what is the an and bn outputs.
Okay.
Okay, out it is only considered over the output. If you see in the diagram, there is no dn. If you see
Yeah.
in this table, there is no dn. Till the output, there is no dn. Till this point, there is no dn. Okay, so if you are talking about this one, at this no dn. Only one input x is defined, and that x is used to implement dn. This x is used to implement the dn. This x and this. Okay. Now the same you can implement with the JK also. What will be changes? What are the changes? If you are taking this one, Okay. Now what are the changes? Only the change is the excitation table. So JK for JK and for JB. Okay, that is only for the excitation table of AN and AN bar, AN plus 1, and that is for BN and BN plus 1. Okay, in the D only one flip flop are considered, so we are saying that DN or DA, you can use that one, DN and DA. Okay, now JK we use two inputs, so J and K. So I'm using for the when we are using the excitation table of AN and AN, using AN and AN plus 1, we are representing as the JK, J and K. If when we are using the BN and BN plus 1, we are using the JB and KB. Okay. Now what is the excitation table of JK? So when 0 0, Qn is 0, same. 0 0 1 1. Okay. 1 0, Qn is 0, J is always 1. Sorry, 0 1. Qn is 0, Qn plus 1 is 0. Qn is 1, again Qn plus 1 is 0. For 1 0 1 1 0 1 1, and when JK 1 1 0, it becomes 1, and 1 JK 1 1, it becomes 0. Okay, so with the help of this one, can I draw the excitation table? That is a Qn plus 1, J and K. So 0 0 0 1 1 0 and 1 1. So 0 0. Okay, two conditions. So J is 0, K is 0, and K is 1. So 0 cross 0 1, 1 and 1, two condition. J is 1, K is 0 and 1. So 1 cross 1 0. This one, this one, and this one. Okay, this one and this. So now J is 0 and 1, K is 1. Okay, so cross 1 and last one and this one. Okay, K is 0, J is 0 and 1. Cross 0. Okay, now 0 0 0 cross 0 0 0 cross 0 0 0 cross 0 1 1 cross 1 0 cross 1 1 1 cross 0 1 0 cross and 1 1. Okay, similarly for JB and KB, 0 and 0 0 cross 0 and 1 1 cross 1 and 0 cross 1 1 and 1 cross 0 0 0 0 cross 0 1 sorry 0 0 0 cross 1 0 cross 1 and 1 0. Okay, now draw the K map for J, K, JB and KB. If you are using the K map, okay, now draw the K map for J. Okay, so 0, 0, 0, 1. 1 is where? 0, 1, 1. Okay, then cross all cross. So this is the 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Here is 1 and remaining all are cross. So this is only the equation. So JA is nothing but BN time X. Okay. Similarly for K. Similarly for K. Again input is the AN, BN X. Now starting a 4 crosses, then 1, fifth is 1, fourth is 1, fifth is 0 and sixth is 1. So first 4 process, then fourth is 1 and sixth is 1. Now create a group of these and this one. So what is the K? K is nothing but X bar. Okay. Similarly, we draw the K map for JB and KB. So JB, AN, BN and X. So 0, 0, 1 is 1, 1, 2x, 3x, 6 and 7x. Okay, 1 is 1, 2 and 3, 6 and 7. Okay, 0, 4, 5 is 0, 0, 0. Yeah, this is that thing. Okay, now again 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. A group of 2. Okay, so JB is what? AN bar X. and last is KB. 0 1 is X, 2 is 1, 6 7 is 1, 2 is 1, 3 is 0, X X, and 4 5 X X, 6 and 7 1. Okay, so basically one group is this one, group of 4, and one group is this one. Okay, so when the lower row, so KB is what? That is the AN plus when it is a group of 4, this corner side, so it's the group of X bar. Okay, so in this way you can write the equation of 4 J, K, JB and KB. Now your flip flop is what? This is your flip flop AN, AN bar, J, K, then BN, BN bar, JB, KB. Okay. Now what is J? BN dot X. So BN comes from here and X comes from here. Ending of this one, this is the J. Okay. Now what is the K? With the X, we are taking the one NOT gate and connect with the K. Okay. What is the JB? AN bar we are taking, and X, similar X we are taking. Take a AND gate and connect as a this one. Similarly, what is the KB? The AN we are already VN taking. Okay, AN taking from this one. X is taking from this side. Take a NOT gate. Implement one OR gate. Connected here. Okay. So this is your diagram. Now any doubt? Where we require the excitation table? Any doubt? Now it is clear. Hello. Hello.
Yes, sir, you're audible.
Have any doubt? No doubts? So I think we stop here.